Well, greetings, mathletes, and welcome back. As promised, we are going to be graphing rational expressions today, or rational functions in this case. Now, your book goes through this 7-step process. Honestly, 7 steps is just too many things to remember. I like to, we're going to cover the same process, but we're going to be grouping these things into 4 categories instead of 7. And we're just kind of clumping it. It makes it a little bit easier to remember what you need to do. So let's go ahead and get started here. So when we're graphing rational expressions or graphing rational functions, oh, okay, there it is. There's usually 4 things you're looking for. You want to see if there's any symmetries, right? And that could be odd, even, or neither. Now, I'll be honest with you. When I'm graphing rational functions, I very seldom turn to symmetry. I believe that this is being pushed in here so that you can have a little bit more practice with it more than anything else. Basically, the way you end up using it, um, it it helps you generate points is what it does. If you need to get a point, if it's an even function, remember that what the criteria is for an even function is that if I plug in negative x in for x, I still get the same function back. And that comes in useful for functions. It's usually more useful in things like trig when you want to just change something from positive to negative. You know it comes out to the same value, so you can switch a negative x to a positive x. And if it's odd, um, f of negative x, well, it basically means you can factor the negative out if it's an odd function. Um, although it's often not factoring, it's something else. But nonetheless, it ends up being the same thing. Now, so we'll go ahead and check these just to check them, but it's not going to be a major issue as far as helping us graph. Now, the things that are going to be important to us to graph: intercepts, right? X and Y. For a y-intercept, you just plug in 0 for x, right? It's the same thing you do for lines. It was the same thing we did for quadratics and polynomials. It's the same thing for all functions. If you plug in 0 for x, you are finding a y-intercept. X-intercepts, basically you're going to end up wanting to solve f of x equals 0. So you're going to solve it for x. Now, asymptotes. And this is probably going to be the big new discussion this time, is how to find these asymptotes. It has to do with the division we did, that we're going to be using that. But there's going to be 3 kinds: horizontal, vertical, and slant. And those are diagonal asymptotes. And we'll see some of those as well. And we'll figure out how those work. Because not all asymptotes are straight up and down or just horizontal. And actually, we're not going to be covering them today, but not all asymptotes are lines. Sometimes you can approach a parabola as an asymptote. So those things happen as well. But these are going to be the main things that we go through. And then that 4th category kind of piggybacks on asymptotes. It actually has to do with both intercepts and asymptotes, but these are holes in the graph, right? We're going to be looking for holes as well. And basically when we find a hole in the graph, we literally put a hole in the graph, right? It looks like that. And so we're going to be playing with these 4 categories. And you can see, you can break this down into 7 steps if you wanted to. You can probably break it down into 12 steps or 15 steps or whatever, but it's really just these 4 categories of things we're looking for. And most of them are related to each other. The three over here on the right are going to be the ones that we use most extensively, but we will be checking symmetry as well. Okay, so let's go ahead and just jump right in with an example. I think that's probably the best way to get going here. Okay, so let's say we want to graph this function. Let's say we got f of x is equal to x squared minus 4x minus 5 over x squared minus 3x minus 4. Now, it turns out there's both forms of this are actually quite useful to us. And when I say both forms, I mean with the polynomials multiplied out and with them factored as well. So it's good to look at both of those because you get information from both of them. So if I factor this numerator, I get x plus 1 times x minus 5. And if I factor the denominator, I get x plus 1 times x minus 4. Okay, so there's information in both of those pieces. I always like to start out by factoring just because, since we're going to need both pieces. So first, let's talk about the symmetry. We'll get that out of the way. So f of x, we want to plug in, we actually want to make f of negative x and see what we get. Okay, so that means that we're going to take negative x, square it, minus 4 times negative x minus 5 over, let's see, minus 3 times minus x, and then it'll be minus 4. Okay, and so if we simplify this, let's see, well, if I square a negative x, I just get x squared. Here I have a negative times a negative, so that makes it plus 4x, and that would be minus 5. And let's see here. So that makes that positive x squared. And that makes that plus 3x and minus 4. So if we actually found, because what we were looking for to see is, did we get negative f of x or did we get f of x back? If we got either of those things, we can say whether it's odd or even. If we didn't get those things, then it is neither. So let's look at what f of negative x would look like. We know what f of x looks like. It looks like the original function, which this doesn't. So it's definitely not this one, right? It's not even. Now, if it were odd, now you have to be a little careful here because remember with fractions, if I have negative 3/4, that is not the same as negative 3 divided by negative 4. Right? Because negative 3 divided by negative 4 is positive 3/4. So you only get to apply that negative to either the top or the bottom, but not both. Same thing happens with functions, right? When I have a rational expression, if I have f of negative x, I can't write today. If I have f of negative x, that's going to be, I still can't write. We're trying to match this up with the negative of f of x. There we go. That's what I'm trying to say. Really, it's just changing the sign, all the signs in the numerators or all the signs in the denominator, but not both. So most likely what you're going to be looking for is negative x squared plus 4x plus 5 in the numerator, and the denominator would stay the same. Right? So it would look something like this. Now you notice this is not, when we plugged in negative x, we did not get that, right? The signs don't match up at all. These two things are the same sign. These two things are opposite signs. So it's not going to match up at all. All the numbers look the same, but their signs don't match up in a way that I can just switch all of the negatives in the numerator. And so this actually falls under neither. Okay, and that's handling the symmetry. So this particular function doesn't have any kind of symmetry. It doesn't have y-axis symmetry, and it doesn't have original symmetry. Again, those really become much more important when we're talking about sine and cosine and trig functions. Okay, so symmetry, none, right? At least not of the two that we looked for. So the next thing we have on our list are intercepts. Okay, now the y-intercept is found by computing f of 0, right? Now, if you look at your original function here, you notice there's x's in the first two terms of both of these. So those terms are going to cancel out. These last two terms end up being the y-intercept, right? So if I plug this in, I'll just demonstrate it. This ends up being 0 squared, which ends up being 0, minus 4 times 0, minus 5, over 0 squared, minus 3 times 0, minus 4. And you notice that goes away, that goes away, that goes away, and that goes away. It always ends up being, if you want the y-intercept of one of these rational expressions and you have everything multiplied out, that's your y-intercept, right? It's negative 5 over negative 4, which is positive 5/4. So I have a y-intercept at 0, 5/4, which is just a little bit more than 1. That's 1 1/4, right? Now, x-intercepts, you have to be a little careful with the x-intercepts because this can be, if you notice, this can be simplified, right? I can cross out this 1 from the numerator and the denominator. Again, when these things show up, it actually ends up being a hole in the graph later. So I'm going to, just for the sake of computing the x-intercept, I'm going to cancel those two things because I know they'll go away. And I can just look at the numerator. So what I'm going to do is set the numerator equal to 0. And the numerator right now is x minus 5 equals 0. And that happens when x is equal to 5. So now I have an x-intercept. Notice you could have more than one of them, right? If you ended up with more than one factor in the numerator, you could have more than one x-intercept. So the x-intercept is at 5, 0. Okay, so we have two things already. That's actually pretty nice. So we're going to need to keep those things stored away. Okay, so we have x and y intercepts now. And I wish I had a full whiteboard right now because I'd love to leave these things up here. But I'll rewrite the list when we actually get to the part where we're graphing. Normally, I keep a graph going and add these things as we come up with them. But we're just not going to be able to do that this time. So let's go ahead and clear some of this off. Okay, so we have talked about symmetry and intercepts. Now we need the asymptotes. Okay, so asymptotes. All right, so vertical asymptotes. Those things happen where the denominator equals 0. And it's equals 0, where it's not canceled out like this x plus 1 is. Okay, so what we can do, if I want to know where the denominator equals 0, well, I have two candidates. This one canceled out, so it's just going to be where x minus 4 equals 0. And you would do this with any factors that didn't cancel out, which means that I have a vertical asymptote at x equals 4. Okay, so that was actually pretty straightforward. You just set the denominator equal to 0 and solve. So I have a vertical asymptote at x equals 4. Now, horizontal and slant asymptotes. Now, it's kind of interesting the way this works. It really does help to look at the degree of the two polynomials being divided up here at the top. right? There's two polynomials being divided here in f. So the way this ends up, let's just generalize this first. So if f of x is equal to p of x divided by q of x. Okay, so we just have these two things. So vertical asymptotes happen where q of x is equal to 0, right? Horizontal asymptotes are going to depend on the degrees here. So if the degree of the numerator, and I'm just going to use this for the degree, so if the degree of p of x is less than the degree of q of x, right? So the degree of the numerator is smaller than the degree of the denominator. The horizontal asymptote is y equals 0. It's the x-axis, period, no matter what. That's not what's happening here, though. What's happening here is these two guys are the same degree. So if the degree of p of x is equal to the degree of q of x, then the asymptote is at y is equal to an over bn, where these polynomials can be written an x to the n plus dot 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 over bm. Oh, bm x to the m plus dot 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 dot, right? So basically, if the degree of the numerator and the degree of, if m is equal to n, then all you have to do is take the ratio of the leading coefficients, okay? Now, if the degree of p of x is greater than the degree of the denominator, you need to divide. That's where your slant asymptote is coming from. And we'll talk about how to get a hold of one of those in a little while here. But this is basically what you do to find your horizontal and slant asymptotes. You look at the degrees of the polynomials, and it will have everything to do with those degrees and the coefficients. So that's what you want to mess around with. Now, write this down. I'm going to erase it right now. You will need this information. If you have to, pause it so you can do this here. Okay, so we have all that, and well, actually we have the vertical asymptote. So let's go ahead and clear that off. And so let's see what we can do about our horizontal asymptotes. There we go. Let's try this again. It's horizontal because these two guys are the same degree, right? It's an x squared and an x squared. The leading coefficients are 1, which means that the horizontal asymptote is at y is equal to 1 over 1, which is 1. And so it's just these two coefficients that I'm dividing here. So it's the leading coefficient of the numerator divided by the leading coefficient of the denominator. That works as long as these powers are the same. If they are not the same, you're in one of those other categories. Okay, so we have a horizontal asymptote at 1 now. So that should take care of all of our asymptotes, and we should be able to start graphing now. So let's go ahead. Okay, so let's start putting in some of the things we have. I just kind of re-summarized everything we just found, that we don't have any symmetry. We have our y-intercept, our x-intercept, our vertical asymptote, and our horizontal asymptote, all sitting right here. So let's just start putting this stuff in. So first off, 0 5/4 would be just a little bit, oh, that's the eraser. Okay, 0 5/4 would be about right here, right? Just a little bit more than 1. So that's my y-intercept. My x-intercept is at 0 or 5 0, so that puts it right there. Now, our vertical asymptote is here at x equals 4, which would be here. Right? And our horizontal asymptote is y equals 1, which is here. So what we have to do now is figure out where everything else goes. Now, there's one thing about the vertical asymptotes. Vertical asymptotes can either be odd or even. And so I'm going to draw in what it looks like when it's odd, and I'm going to draw in what it looks like when it's even, and then we'll look at how to tell. Okay, so if it's odd, what it'll end up doing is going up on one side and down on the other when it approaches this. So they'll go opposite directions. If it's even, they both go the same direction. They'll either both go up or they will both go down, one of the two. It's the same thing, and it's the same thing for any rational expression. So the way you tell if it's odd or even is you look at the factor that gave you that asymptote. In this case, it's an x minus 4, and the exponent on that is a 1, which is an odd number, which means they go opposite directions. If it were a 2 or a 4 or a 6, that would make it even, which means they go the same direction. Okay, so because that's a 1, we know these will go opposite directions, and we just need to figure out which way they go. Okay, so I know, looking at this, that this is odd, right? And that means they go opposite directions. Now, let's reason a few things. This is where the reasoning part comes in. Once you have these things pieced together, now you have to imagine what would happen in each case. So we know this is a point, and I'm going to be heading towards this asymptote. Now, first of all, horizontal asymptotes, a lot of the time they have this reputation that they can't be crossed at all. It does not. A horizontal asymptote can be crossed, right? It just means that the function still gets closer and closer to it as you go farther out. So it's entirely possible that this thing does this and goes down, right? It absolutely could happen. If we take a good look at this, though, that would mean I would have to cross the x-axis. And if I cross the x-axis, there should be another x-intercept, but there isn't one, right? Since there is no other x-intercept for this to cross, that means it has to go up. So that means this guy does this, right? And that automatically means that the other side does this and goes down. Okay. Now the horizontal asymptote, it's always hard to tell. It could conceivably do something like this and like pass the asymptote and then zoom in on it again. But we don't know that. So we're just gonna draw in what we do know, right? And just go from there. As long as we have something that's in the ballpark, we'll be able to identify what we need. Okay, now there's one other thing. We talked about a hole in the graph, and we actually have one because of this, right? Those two things canceled. Now, x plus 1 equals 0 means that we have a problem at x equals negative 1, okay, which is here. Because this is a 0 of the numerator and the denominator both, and it completely cancels out. What that means is there is no value for this function at negative 1. Negative 1 causes a problem. So this is how we handle it, right? We're just going to make a little hole here at negative 1. And we'll just have a hole in the function, right? There'll just be a hole in the graph. Wherever that function value is, we're just going to erase it and put a little hole there. And so that's what this function looks like. We did a lot of work to get here. Now, hopefully it'll go a little bit quicker as we go, because a lot of the time, well, you'll notice I went through and I explained odd and even asymptotes. I went through and talked about the different cases with the degrees of the polynomials and how that affects the horizontal asymptote. And so we spent a lot of time talking about those things. These actually work a lot quicker than this as we go. So let's go ahead and look at another example, and we'll see what we can do with that one. Okay, so let's look at another function. Let's say we have h of x is equal to x cubed plus 1 over x squared plus 2x. Okay, so it's also convenient, of course, to have the factorization here. So that's the sum of cubes in the numerator. So that's x plus 1 times x squared minus x plus 1 over, and then the denominator would be x times x plus 2. Okay, so we have everything laid out here. Now, you notice nothing cancels, first of all. Right, there's no common factors between the numerator and the denominator here. So we're not going to have to worry about any holes in the graph this time. But we can deduce a few other things. So let's start with the symmetry. And I'm going to try this a little different this time. I'm going to do the work here in this side spot and then see if we can graph anything. I'm going to put it on the graph as we find it this time. So symmetry. Let's look at h of negative x. Right? So that would be negative x cubed plus 1 over negative x squared plus 2 times negative x. And let's see here. So that'd be negative x cubed plus 1. Well, there's already a problem. There's no way to rectify negative x cubed plus 1 with x cubed plus 1. But, so that'll be x squared and then minus 2x. Yeah, and there's really nothing I can do here. These aren't exact opposites. It's like some terms are opposite terms and some terms aren't. So this doesn't have any symmetry whatsoever. Okay, so there's no symmetry. And I'm just going to write that down. Okay, so no symmetry. So we'll start there. Then, the next thing on our list are intercepts, right? And so remember, you're going to have y-intercepts where x is 0. You're going to have x-intercepts where the numerator is equal to 0. Okay, so f of 0, if we look at this, well, we already have a problem. F of 0 is undefined. Okay, that means it doesn't cross the x-axis whatsoever. If you plug in 0 here, I end up with 1 over 0, right? And that's the definition of something that's undefined. So there are no x-intercepts. Okay, so for the y-intercept, oh, excuse me, I can't believe I just said that backwards. F of 0 gives you the y-intercept. There we go. X-intercepts is f of x is equal to 0, and f of x is going to be 0 where the numerator is 0. So this is going to be x cubed plus 1 equals 0. Well, we're going to need the factored form. Now, here's the thing. When you factor the difference of cubes, that second term there always has complex numbers as its solution. So even if you can go through and try to solve it if you want, but you're not going to get a real number, which means it's not something that shows up in our graph. The only part of that's actually going to give us anything is the x plus 1. When x plus 1 is equal to 0, this whole thing is equal to 0. So this is x equals negative 1. So we have no y-intercepts. What we just found out is we have an x-intercept at negative 1. Okay, so we'll add that in there. That's the first thing we can actually graph. So I'm going to write that down now. So x-intercept is at negative 1, 0. Okay, so we can plot that. So that's a point I can get. Okay, so we have that. Now, asymptotes. So vertical asymptotes is where the denominator is equal to 0. And it's convenient to have it factored. So you have x times x plus 2 equals 0, which means that either x is equal to 0 or x plus 2 is equal to 0, and x plus 2 gives us negative 2. So we have two vertical asymptotes, one at 0, and this explains why plugging in 0 gave us an undefined value, why there's no y-intercepts. Actually, let's do that in red so it stands out. And then I have one at negative 2 right here. All right, so I have two vertical asymptotes. Now, I have those marked in there. Now we need, I'm going to go ahead and back this work up. Okay, so the vertical asymptotes are x equals 0 and negative 2. Okay, so we got those. Now, horizontal or slant asymptotes, right? That depends on the degree. So when the degree of the bottom is bigger, you have a horizontal asymptote at 0. When they're the same degree, it's the ratio of the leading coefficients. And now this one exceeds the numerator by exactly 1, which means we have a slant asymptote. So we need to do the division. Now I didn't show you the division of something that looks like this, but it does not work with, what do you call it? You can't do it with synthetic division. So we're going to have to do this division. So we'll do x squared plus 2x into, I'm thinking this needs to be lower. X squared plus 2x into, now I need to add all these things in there. I got x cubed plus 0x squared plus 0x plus 1. So I need to see what I get when I divide by this thing. Now, you ask yourself the exact same questions you did before. You say, okay, so I'm just going to concern myself with the leading term. X squared times what gives me x cubed? Well, the answer is x. And if I multiply through and subtract, I get minus x cubed minus 2x squared. So those cancel, and I get my minus 2x squared here. And then I'll bring down my plus 0x. And let's see here. We got x times minus 2 will give me minus 2x squared. So if I multiply that through, that gives me plus 2x squared plus 4x. And you notice already, even before I got the rest of this, I have 4x, and then I'm going to drop this down as a plus 1. X squared doesn't go into 4x, does it? Which means that this is my remainder. So x minus 2 is actually what I want to get a hold of. This remainder piece, right, this piece that's hanging out at the end, which would be 4x plus 1 over x squared plus 2x. As x gets bigger and bigger, this part gets smaller, and all you're left with is the function behaving like x minus 2. So this is one of those cases where the remainder is what you don't care about. All I care about is this first part. So my slant asymptote, right, is going to be y equals x minus 2. And it's whatever you get when you do that division. It's the quotient part of it, not the remainder. So if I'm going to graph that now, let's see here. I have a y-intercept at negative 2 and a slope of 1. So that means that this guy comes off at a diagonal this way. So basically, you just throw away the remainder and graph whatever's left of the line. Right? That's what you're looking at. Okay. Now we have all our asymptotes in place. And we have our intercepts. Well, there's only one, but that's okay. Now what we have to figure out is how everything else behaves, right? That's the idea now. So it's going to be real hard to figure out what goes on without having a couple of extra points. So what I like to do is just pick something that's fairly convenient, that's clearly in one of these regions, and plug it in and see what I get. So I think I'm going to plug in fact, let me get some of this off here because I'm going to need all this space. I'm going to plug in, that's an eraser, -3, and just see what I get. Okay, so -3. So we've got that plugged in here, and oops, that's not a minus, that's a plus. There we go. So what we end up with is -26 divided by 3. And so if I look at that, if I actually divide that by 3, that gives me, what, 8 2/3? -8 2/3. That makes it a little easier. That means -3, the point is down here somewhere, which puts it in this region between these two asymptotes here. So I don't know exactly what they do, but I know it's going to approach this asymptote from this side and curve somehow and do this. Okay, so that means with this asymptote right here, now remember this is an odd asymptote. Because it's an odd asymptote, if this side moves down, that means the other side has to go up, which means that, actually I wanted to do that in purple. That if this side goes down, this side has to go up, right? And this is an even root, which means it doesn't bounce off. It goes straight through. Don't get caught up with the fact that it's crossing the asymptote here. The asymptotes are what happens as you go away from 0, not what happens near 0. Okay, now this one goes down, right? And if this goes down, that means the other side has to go up. And I don't have any intercepts on this side, so that means it's going to just do this, right? It should go. So it approaches this asymptote from this side, this one from this side, and the whole graph of this thing ends up being what's in purple here. Now, if you graph this on your calculator, you won't see the asymptotes, although it will try to connect the dots between a dot on here and a dot on here, so it's kind of written in. But yeah, these things can get messy. You're just kind of piecing this information together as you go. Now, the way your homework breaks it down is it asks you to find all these things individually and then asks you about the graph. Okay, so it's not a bad idea to have some graph paper out and just start sketching things as you figure them out. And you can eventually, especially if it's multiple choice, you can narrow down which graph it has to be just by what's missing from the other ones. All right. So let's take a look at another example here. And I think we've looked at some of the more complicated things. I actually want to just kind of take this back down to something a little more bite-sized here. Okay, so we're going to take a look at this one. And like I've already shown you guys how to check the symmetry. I'm not going to worry too much about the symmetry part of it because it's really not something that gets used all that much with the graphing, to be honest with you. But I'm going to go ahead and just kind of piece the information together and put it on the graph instead of making a list. Because honestly, the graph is a good summary of what you've learned so far. Your homework will break it down into pieces, like I said, but when you're actually graphing one of these things, you don't think about it in steps. You just start finding things. You check the numerator, check the denominator, and look for things to cancel, mostly is what you do. And then if you need a little more information, you plug in some points. That's generally how it works. So first thing we want to check for are intercepts. Let's see here. So we're going to need this stuff all factored out. So let's say this would be x minus 1 times x minus 3. And then down here, this is going to be x plus 1 squared. Okay, so I can see from the numerator that I have zeros at 1 and 3. Right? I can see them right there. Zeros of the function are x-intercepts. Okay, so I'm going to mark that in. I got 1 here at 1, and I have 1 here at 3. Okay, so that's good. Now, asymptotes. Okay, so asymptotes, the vertical ones, I'll just say vertical asymptotes, are going to be where the denominator is equal to 0. And we have the same factor twice, and that factor is going to be 0 when x is equal to -1. You notice I haven't done any computation yet. That's what's kind of fun about these, is that once you have it factored, you really can just look at it. All that other stuff, it's important to know how to write things technically. But if you're just going through it, you don't need all that technical writing. You need the technical writing when you're communicating new information to another mathematician, right? You want to organize things a little more neatly. But if all you're after is the graph, then hey, whatever. And I want to point out too that this time the exponent is 2, which makes this even. And even asymptotes, that means either both things go up like that, or both things go down. Bottom line is they go the same direction, right? Okay, so we have zeros, we have asymptotes. These are the vertical ones. Now, horizontal asymptotes, we need to look at the degree of these two polynomials here. And they are the same degree. Since they are the same degree, we just look at the ratio of their leading coefficients. So the horizontal asymptote, I guess I should... There. The horizontal asymptote is going to be at y equals 1, because that's the ratio of 1 divided by 1. So, let's see, y equals 1 puts it right here. Well, this should be a very interesting plot. Whoa, I think I bumped something there. I think I just scrolled. Okay. Now, we got some interesting information here. One thing that I can actually deduce from this is that if I end up doing this in this quadrant, right, if the function ends up doing this, I have a little bit of a problem here. It has to cross the x-axis to be able to approach this asymptote, right? If it crosses the x-axis, that means I missed one of the zeros somewhere along the line, because there would have to be a 0 out here on the other side. So let's plug in a value that is on the left-hand side of this asymptote to see what it does, and we'll go from there. So let's see here. The asymptote's at -1, so I'm going to plug in -2 to the function. So we're going to look at f of -2. Let's see, f of -2 would be -2 squared minus 4 times -2 plus 3. That's a 3, I swear. There. And then down here, -2 squared plus 2 times -2 plus 1. Okay, so we just need to figure this out. So we have 4 plus 8 is 12, plus 3 is 15. So it's a positive 15. And then down here I have 4 minus 4 plus 1, which is 1. So that means we have the point -2, 15. So at -2, I'm way up there. So what that tells me then is that this guy goes up, right, as I move this direction. And so that means it approaches this other asymptote from this side. Now, we need to figure out what happens here, right? Because this seems weird to have these two zeros here and not knowing exactly what's happening. Now, one of the things we didn't find that would be very useful is to have a y-intercept, because that will tell us which side of this asymptote we're on here. So again, and I think I pointed this out, f of 0 gives us our y-intercept. And that's going to 0, if I look up here, That's going to zero the first two terms of both of these out, and what I end up is 3. So that means I cross here at 3, and I think we can see what's happening now, right? It has to do this, and this is where you have to resist the urge to not cross the asymptote. I have to get to these two roots, don't I? Now, these are both linear roots. And remember, if you have a linear root, they just cross the x-axis like that. If you have a squared root, it's going to bounce off the x-axis, and any other odd root is going to do a jig-jog as it goes through. These are both linear roots because both of them have exponents of 1, the factor that gives you that. So that means what it has to do, let's see if I can draw this here. Try this again. It has to come down this way, cross this, come down here some amount. We don't know how far down it goes. And then come back up and do something like this. It may cross that. It may cross this asymptote and then come back down to it as well. You really can't tell. But this is what the graph of this function should look like. Right? And you notice you just kind of have to deduce things. Remember that once you have all of your zeros, right, all of your x-intercepts, you should not be crossing the x-axis anywhere but at the x-intercepts. Those are the only places you're allowed to. So if you find yourself in a situation where you have to cross something you know you're not supposed to cross, you've probably done something incorrect. So we've gone through most of these examples, and this, again, this is one of those subjects where it's very hard to teach this in a methodical, step-by-step way because every problem is different, and sometimes it's a lot easier to do things in a different order. In any case, yeah, I think that's everything we need to cover here. So, yeah, so until next time, keep your pencils and your wits sharp.